let me record now. If the where we were, the population distribution is normal if the pattern of the points is reasonably close to a straight line, and the points do not show some systematic pattern that is not a straight line pattern. Otherwise, it's not a normal distribution. So let's read this, the last paragraph. The population distribution is not normal if either or both of the following two conditions are met. The first condition, the points do not lie reasonably close to a straight line. The second one, the points show some systematic pattern that is not a straight line. Okay, for example, the points give you a like this pattern. That is a systematic nonlinear pattern. It's not a straight linear pattern. Then you would conclude the population is not normal. All right. So this part doesn't have much thing to cover, to be honest. The homework questions are pretty straightforward. Mainly, those questions are mainly about the three steps in the procedure of assessing normality. In your homework, you are not required to construct the QQ plot on your own. I look at all the homeworks. They will give you the graph and let you to determine if the population normally distributed or not. However, your review has a question, requires you to construct the QQ plot based on the given sample, and then determine or assess the normality of the population. Also, your exam 2 has one question, requires you to construct the QQ plot on your own using technology, and then determine or assess the normality. So we are going to spend time on that, okay? Yeah, I just found a question pretty close to the question you're gonna see on the test. Our technology, again, TI-84 calculator, all right? You do not have a StatCrunch available during the tests. With the lockdown browser, your Excel is not available either. So the only technology you can apply is the TI-84 calculator. So please get your TI-84 calculator ready. So let me introduce what happened to this problem. So this problem gives you a data set or sample, gives you a sample, and ask you to construct the QQ plot. That actually asks you to choose which one is the QQ plot. You would not be able to know which one before you actually have the QQ plot constructed using the technology, right? Yeah, so we have to construct our own and compare our plot with those four and choose the one that is the same with our plot. Yeah, that's the first thing. And then based on the QQ plot, the pattern, yeah, linear pattern or nonlinear pattern, and the guideline we just shared, we just went through to complete this multiple choice question. Yeah, is normal or not normal, right? Yeah, this section is about determine if the population normal or not based on the given sample. All right, TI-84 calculator. The first step is to enter those values in your list 1. Okay, yeah, let's all enter those values to list 1 just for convenience. Technically, you can use any one of the 6 lists in the TI-84 calculator, but let's just use L1. So I'm going to go to Stat. All right, and then select Edit. I have something in my list 1, so I'm gonna clear that list and then enter those values in it. Let me count how many values do I have. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So each column I have 10. I have 4 columns. So I'm going to have 40 values. Yeah, in other words, the sample size of the sample is 40. It's gonna take me a little while. Everybody do the same thing, okay? Yeah, I'll be quiet, not disturb you. Let's correctly enter the 40 values in list 1. Okay, I finished. All right, I finished. You know what? Let me connect my document camera. I think I want to show. Even this is troublesome for me. It's better that you see my calculator. I'm going to share my camera. HD camera. Okay, guys. So this is my calculator. It's a little blurry, right? Okay, this one's better. So I just entered the 40 values in the first list of the TI-84 calculator. And what do we do next? Next, we're going to enter second y equal. Right here, this key, upper left key is y equal, right? Above the key, you would have the blue words says, this is very small, plot, stat plot, what is it? Stat plot, yeah. You are going to do, what is x? What's the question? What is x? I don't get it. Dustin, what is x, guys? So you're gonna enter second y equal, all right? Second y equal. And then you should see this, you know. We're going to select number 1. And you're going to turn on the plot, number 1, and then go down, and you will see bunch of different type of graphs, right? Yeah, that is a scatter plot. It's very tiny for me to see as well, this angle. And you are going to use the bottom right plot, this one. I don't know if you can see it. This one, bottom right. Like a linear pattern, right? That is the QQ plot. So you're gonna enter, select that, confirm that one. Confirm that one. And then you're gonna go down. Where's my calculator? You're gonna go down to data list. You enter L1, okay? You enter L1. And you choose X or choose Y. Let me look at the question. We are going to use X because the horizontal scale are the values of the data. So we are going to choose X here, and then you can, depends on your preference, you can choose the mark. I use the big dot. Am I clear, guys? I'm sorry, the technology isn't the best. Let me fix this closer. Okay, do you have those? Plot 1 is on, and this one is the one we need. This, and then the list 1, that's where we store the data earlier. And then choose X. That decision is made based on the ABCD 4 answer choices, and then choose your mark. Okay, very good, very good. Okay, and then we are going to enter this key, graph. Okay, graph. You might not see the same thing with mine because I do the same thing before. If you don't see that, it's okay. All you need to do is to go to zoom. Zoom is the middle key, and then go down number 9. Zoom stat. That would adjust the window for you. Yeah, because mine's already adjusted, so you would see that even without adjusted again, we see that already. So this is the QQ plot we have. Yeah. This is the QQ plot we have. All right. Do you have the same thing, guys? Okay, awesome. Yeah, that's the QQ plot. All right. So now I'm gonna share back. No, you don't have Miranda. And let me do it again. Yeah. So you firstly go to stat, right? And add it. You're gonna store all the 40 values in the first list. Yeah, be very careful. It's possible that you enter something wrong and ruin the whole thing. So be very careful. Take your time. Yeah, that would be the tedious part, but get that done. Yeah, get that done, because that's how do you tell the calculator what do you need, right? Yeah, you have to tell the calculator what do you need. And then we're going to go to second, this key. Second, okay, I enter the values. Okay, and then you go to second y equal. Do you have that? Yeah, okay. And then enter. Do you have that? Okay, awesome. You need to make sure it's on. Is if the calculator only blinking on, you are not confirmed. That doesn't count. You have to confirm it's on, and then go to the graphs. you're gonna select the one right below the histogram. 1 minute, it shows X and Y lists. I don't get it.
Might have the histogram instead of the straight line plot if it's both the X list and the Y list. It's a different type.
So you have 6 graphs. Do you see that? The last one, the one in the bottom right, right below the histogram, that's the one you need to confirm. Okay. Any progress? Okay. I clicked the first one. That was my issue. Oh, yeah, that's scatter plot. As you can see, mine's blinking there, right? But I can move to the right and to the right and to the right and then to the right and then to the right. Now it's blinking on the QQ plot, and then you have to confirm it. You know, if you don't confirm, it's gonna go back where it was. And then you go down. Yeah, I think it's default as L1. That's why I want you to enter the values in L1. Do you have that? Okay, so and then you choose X. Yeah, this decision is made based on the answer choices. Sometimes the context of the question will tell you choose X or choose Y. And then the marker doesn't matter. I just use the biggest, the circles. All right, you ready? Once you have those confirmed, you're gonna click this key. Now push this key. The very upper right corner key, graph. If you don't see the same thing, that's fine. All you need to do is go to the middle key, the one here, stat, zoom 9, yeah, zoom, and then go down. Oops. Go down, go down 9, zoom stat, confirm zoom stat. And you should have the same thing with mine. Oh, okay, we talk about that later. How about, yeah, you can stay after the class. So if you have the same thing, yeah, then let me switch back. We're gonna look at the 4 answer choices and choose the one same with our. Okay, here. So look at your QQ plot and look at those 4 answer choices. What do you think? Which one is close to ours? From what I see, I think it's B. B as in banana. What do you think, guys? Yeah, same. Okay, very good. So we agree it is B, right? It is B, so you choose B here. Yeah, choose B here. Yeah, and then you can assess the normality by looking at the graph. Answer choice A, the distribution is normal. The points show a systematic pattern that is not a straight line. The sentence is contradicted itself, so we do not choose A. B, the distribution is not normal. The points show a systematic pattern that is not a straight line. I think that I'll leave that there. C, the distribution is normal. The points are reasonably close to a straight line. Not that close. This one is pretty close, but ours is not that, right? So I will not choose C. D, the distribution is not normal. The points are reasonably close to a straight line. Okay, that's contradiction. So I would choose B again. Yeah, because it's like the pattern is kind of a concave down pattern, right? Yeah, and then go up a little bit. Yeah. So it's not the linear pattern isn't pretty strong or reasonably close to a straight line. All right. Yeah, you guys, do you agree? We choose B again for that last part of the question. Okay.
I have a question. Will we have to press the Zoom start every time? Or should it just
Zoom
come up?
step. Yeah, Zoom 9. Zoom step. Yes,
Or
if you
yes.
don't have, yeah, if you don't have what you need, if you're like nothing or weird, then you have to adjust the window. Yes, you do have to do that. And it's always good to do that. Adjust the window, then you can see the whole picture better. Did I answer your question?
Yes,
Did I?
thank you.
Okay, no problem. So, as I
I have a
said,
question about that.
yeah.
If there are like several outliers, will that automatically just dismiss it as being normal?
Oh, that's a very good question. Yeah, I think if the number of outliers is 0 or 1, in this case we have a 1 outliers, that's fine. The decision is not based, in this case, because there's a 1 outlier. We made a decision because of the pattern, because those dots are not very reasonably close to a straight line. This one C, if we got a C, if after we enter the value and we got this, then I would say yes, it's normal, because those dots are so closely arranged around the straight line, right? Reasonably close to the straight line. The linear pattern is so obvious, but we don't have that. We have a B, and it's not a straight linear pattern. It's not linear pattern for sure. Did I answer your question?
Yes, ma'am.
Yeah. This question is to ask us to assess the normality based on the plot. Yeah, you're good that you notice the outlier, but as long as the number of outliers is not is not more than 1, it is fine. Yeah, as the procedure shows right here, if there's more than 1 outlier, conclude is not normal, right? Yeah, but if you have a 0 or 1 and you proceed, so the question actually assumes it passed the first 2 steps, and we assess the normality based on the plot, QQ plot. All right, guys, any questions? Any questions about this section? Yeah, as I said, when you do the homework of this section, you don't have to construct your own QQ plot. Yeah, but you will see one question in the review. That is because you're going to have one question that you need to construct the PP plot in the text in exam 2. Yeah, so you're going to take that seriously. That's why we spend time on that. I hope you grasp the method. The only tedious part is to enter the 40 numbers. All other parts are pretty straightforward and pretty easy. Are we good? Yes or no?
Yes.
Yes, and I think doing the chapter homework will let us know if we're not.
Yeah, I was muted. Yeah, that's why when I switch back and forth. So you heard me, right, the whole time? Hello?
Yeah, we heard you.
Why is asking me to log in? It's weird. Are you able to see my OneNote?
Yep, we could see your OneNote and hear you.
Okay, perfect. Yeah. Now let's proceed to the next section. The last section of this chapter. Normal as approximation to binomial. Okay, yeah. So this section is about using normal distribution to approximate binomial distribution. Yeah, since this section involves two distributions, yeah, binomial and normal, I think it's necessary to go over the concept. Let's recall what is a binomial distribution. Okay, yeah, let me give you an example, very simple example. Let's consider rolling a die for how many times? For 10 times. Okay, that is my experimental procedure, rolling a die for 10 times. That procedure gives us a binomial distribution. The binomial distribution procedure satisfies four conditions. The first condition, there are unfixed trials. So here we have 10 trials. I rolled the die the first time, that's the first trial. I rolled it again, the second trial, and so on and so on. I roll the die the 10th time, that is the 10th trial. So the number of trials is a fixed number, n. So that's the first condition. Second condition, all the n trials are independent. Our experiment, the 10 trials rolling the 10 dice, are independent. Number three, for each trial, the outcomes can be classified into two categories. One category is success, the other category is a failure. So either success or failure. So here we can say if we say a success is to get number 6, then the failure would be not number 6, right? So the outcomes, we have 6 outcomes for each trial, can be divided into two categories, success and failure. So number 3, that's the third condition. The last condition requires the probability of success remains the same for all the n trials. In our case, the probability get number 6 each time we roll the die remains the same. Of course, every time we roll the die, the probability getting number 6 is 1 over 6, right? Yeah. So if all the 4 conditions are satisfied, the procedure corresponds to a binomial distribution. More specifically, which variable follows or has a binomial distribution? This variable. We're going to use x. The variable x is discrete to represent the number of successes, plural, among the n trials. Earlier, the experiment is just the background or the environment. Here, the variable, random variable, discrete random variable that really has a binomial distribution is this discrete random variable that represents the number of successes among the n trial. All right? Yeah. In our case, x represents the number 6 we got among the 10 trials, right? Yeah, so all the possible values for x include 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 values. Yeah, again, binomial distribution is discrete. The number of the number of values that the variable can assume are finite number of numbers. All right, also we want to go over the notation. In a binomial distribution, yeah, you might remember I always write this x with b and p. Yeah, n and p are the two important parameters in binomial distribution. N here is the number of trials. P here is the probability of success. It remains the same for all trials. Q here is the probability of failure. So it is the complement probability of success. So Q equals 1 minus P. And X here, the little x, is the number of successes among the n trials. Yeah, the number of successes among n trials. So I hope you still remember binomial distribution, all right? And in this section, we are going to use a normal distribution to approximate binomial. Normal distribution corresponds to a continuous. What interesting is normal distribution is a continuous random variable. Yeah, and we are using a continuous distribution to approximate a discrete random variable distribution. So we have a continuity correction to adjust from discrete to continuous. That's going to be a challenging part for this section. Yeah, we are going to take time to tackle that part. All right, yeah. When could a normal distribution approximate a binomial distribution? There are certain conditions need to be satisfied, all right? There are certain conditions need to be satisfied here. The condition is both NP and NQ have to be no less than 5. Okay, if NP, n times P, yeah, the value of n times P is no less than 5, bigger than or equal to 5. Also, n times Q is bigger than or equal to 5. Yeah, we need them both satisfied, okay? If they are both satisfied, then probabilities from a binomial can be approximated by a normal distribution. And with the following parameters. Yeah. So if we summarize this theorem, if for a binomial, if NP is no less than 5, NQ is no less than 5, then we can use this normal distribution to approximate the original binomial distribution. So the conditions are n times P no less than 5 and n times Q no less than 5. Yeah, this part is very important. We are going to talk about that later, okay? There's a website here. I want to show you how could a
So sorry to interrupt, but pretty much to restate that, it just totally has to have a large number of trials then. Is that sort of the long and short of it?
Yeah, you are right.
Okay.
But yeah, if number of trials is up to you, right? Yeah. So even if the n is quite small, you would want a P and a Q both very close to half. But what if P and Q are not close to half? For example, P is 0.9, then Q has to be 0.1. If one of the P and Q close to 1, then the other has to close to 0, right? Because they add up to 1. Yeah, but to counter that, we want an n large enough. As long as the n large enough, both of the two conditions may be satisfied. Okay, so I have a website that I want to show you. It's right here. this. All right, so let's see, how could normal distribution approximate binomial distribution? All right, and do you see n here? N here is 5 right now, right? I can adjust. I can let n be 1. Yeah, and p, this is the value of p. I can also adjust the value of p, right? If we consider binomial distribution that we toss a coin n times, not die. Yeah, this time let's just make it even simpler. Consider tossing a coin n times. If getting head is a success, then getting tail is a failure. Either way, P and Q are 0.5, right? Yeah, that's ideal. Then we don't have to have a very large number of trials. So let's see if P is 0.5. You can see I have P equals 0.5 here, right? If we have one trial, then the distribution just flat, right? Just one trial. And if I change the number of trials, you see that? It's very symmetric and bell-shaped. It's getting larger and larger. It's getting skinnier and skinnier because when n is very large, NPQ, take the square rule. The standard deviation is getting smaller. All right. So yeah, ideally P and Q are both half. That's the best. But what if P is not 0.5? Let's say P is 0.9. I cannot get a 9. How about 0.873? Yeah. So when n equals 16, as you can see, the histogram has a left is very long left tail. It is skewed to the left. But as Kelly just said, right? We just need to make n very large. Yes, exactly. But if we make n very large, as you can see, from a certain point, the left tail, the longer left tail, becomes shorter and shorter, and the symmetric is more obvious and more obvious, right? So we use our own eyes and really see that normal distribution could actually approximate binomial distribution as long as the two conditions are both satisfied. Sometimes P and Q are not very close to half, but that's fine. As long as we make the number of trials large enough, that is in our control, and we are able to use the normal distribution to approximate the binomial distribution. Is that clear, guys? Any questions? Hello? Am I muted? No. Any questions, guys? No questions? We can hear you. Okay. Okay, very good. Thank you, Kelly. Oh, yeah. I like that. Yeah. It's because you can see it in use your eyes, right? And that might give you pretty strong impression. Yeah. How could a normal distribution approximate a binomial distribution? And you use your own eyes, you see it. Again, for the proof part is not our focus. You guys are not mathematical major. Mathematics major students mainly focus on why. They prove like me. When we were in the graduate school, we prove. We just we don't do much calculation. Calculation part is just a minor. Mainly is to prove why. Even is like a very obvious thing. You have to prove it. We focus on how. Okay, how to use it. We don't really focus on too much why. So another thing about this section is the continuity correction. All right, yeah, so I had them boxed here. The binomial distribution is discrete, right? Because the variable that is binomial distributed represents the number of successes among the n trials. Yeah, so the binomial distribution variable has to be discrete and only assume whole numbers. 0 is the minimum value, and then 1, 2, 3, 4, all the way to n, right? Yeah, those are the values binomial distribution variable assume. But now if we use a normal distribution to approximate, a normal distribution is continuous. Yeah, normal distribution, as you can see the density curve, the bell-shaped curve, the domain is all real. So x could be any number from negative infinity to positive infinity, right? Yeah. Now how do we adjust that? We do have to adjust that from discrete to continuous, and the process is called continuity correction. How do we do the continuity correction? We use the 0.5. We use 0.5 to adjust. All right, to compensate, we use a continuity correction with a whole number x, represented by the interval from x minus 0.5 to x plus 0.5. Okay, so let's say roll a die 10 times. Remember the beginning today? Roll a die 10 times. 10 times. And x is the number of success. So x is a binomial distributed. And all the possible values for x is 0, 1, 2, 3, all the way to 10, right? Yeah, on the real number line, we have a 0, 1, 2, 3, 4, 5, 6, 7, 8. Should I have drawn this longer? 9, 10. Right? Those are all the values x assume. And when we use a normal distribution to approximate that, for example, we consider a probability of x equals 5. Yeah. And this is a binomial. Now, how are we going to use normal distribution to find the probability? And we're going to construct an interval from 4.5 to 5.5, right? So we would have a x here now is a normal distributed variable. Is bigger than or equal to 4.5 and less than or equal to 5.5. And this x is normal with mean n times p with standard deviation square root npq. Does that make any sense, guys? That's part of the one example about continuity correction. Yeah, when you use normal distribution to approximate binomial distribution, right? And you have to adjust the single value to an interval. This is an individual value, one value equals 5. But you know, continuous random variable, the probability of a continuous random variable equals one single value is 0. Why is it 0? Because in a two-dimensional space, the area of a line segment, if it's a region, if it's an interval from here to here, right, then the area is the probability, right? But what if you only have one single value? Then you simply just have one line segment. And what's the area of the one line segment? Is 0, because it doesn't have an area. One line segment doesn't have an area. So you have to adjust that to an interval. The way we adjust it is to use 0.5. Yeah, from 5, go to the left 0.5, go to the right 0.5, and we use the interval 4.5 to 5.5. And we do the same thing to all those values that x assume. Then we can have the whole interval from negative 0.5 all the way to 10.5, and we can use the normal distribution to approximate it. Any questions? I think the best way is to use the continuity correction, and I show you how to do that using the calculator. Well, do you have any question about what I just explained right here, guys? Okay, then let's do problems, and you would understand that better. Examples, understand that better. Let me find a question. Value given below is discrete. Number 7. Okay, number 7. If NP is no less than 5 and NQ is no less than 5, estimate this probability. What probability? Probability of fewer than. Fewer than means strictly less than 2, right? Yeah, we have a binomial here, and with n equals 14 and p equals 0.4. This is how do I take a note while reading the question. Yeah, we have a binomial here, and n is 14, p is 0.4. And we are going to estimate this probability. By using the normal distribution as the approximation to the binomial. If NP is less than 5 or NQ less than 5, then state the normal approximation is not suitable. Yeah, some of the questions you will see in my lab math has either n times p strictly less than 5 or n times q strictly less than 5. Then you're going to choose this one, okay? But this question is not. Yeah, we can double check. Calculator, please. Yeah, let's see what is n times p and what is n times q. N times p is 14 times 0.4 is 5.6. It's bigger than 5. Oops. Right? No less than 5. Yeah. And NQ, we know what is Q, right? Q is 1 minus P. P and Q have to add up to 1. It's going to be bigger than that because 0.6 is bigger than 0.4. 8.4. Yeah, also no less than 5. So both conditions are satisfied. All right. Yeah, every time you have to double check that. Once you know those two conditions are satisfied, you are going to apply normal to approximate all right? So we have to the mean and the standard deviation. We have to find out what is the mu and the sigma we are using for the normal distribution that is gonna approximate the normal, the binomial, sorry, binomial. So mu here is n times p. Okay, yeah, in the calculator, you just need to enter 14 times 0.4. You don't have to evaluate on your own, just enter the expression. And the sigma is square root npq. You enter 14, yes, square root 14 times 0.4 times 0.6. All right, so that's the normal distribution we are going to use to estimate the probability. Okay, how are we going to do that? P of x is less than 2. Everybody go to calculator, use the second vars and find normal CDF. Yeah, get that ready, please. Since the probability we are going to find is x strictly less than 2, that means 2 is not included. All right? Yeah, x can only assume 0 and 1. In that case, we're going to adjust the 2 to 1.5. That's the part, that's the continuity correction. So once you see normal CDF, your lower is negative infinity, your upper is 1.5. Yeah, if you enter 2, that's incorrect. Let me explain why it's incorrect. Because if x is normal, is continuous. Yeah, if x is continuous, then for a continuous random variable, x is less than 2, the probability x is less than 2, and the probability x less than or equal to 2 is the same thing. It doesn't matter. However, for a discrete random variable, those two things definitely are different. Yeah, because if x is discrete, like a binomial, then this means x assumes 0 and 1, and this means x assumes 0, 1, 2. How could they have the same probability? They don't, okay? Yeah, again, as a discrete random variable binomial, those two probability are different. But as a continuous random variable, yeah, because we are approximating, right? Yeah, x gonna be a normal, yeah, then they are the same. They are exactly the same. Exactly the same. How do we adjust that? Then we have to let the calculator know x cannot assume 2. In order to let the calculator know x do not assume 2, not this one, not this one, we have to adjust 2 to 1.5. So for continuous random variable, like a normal distribution, and x is less than or equal to 1.5 on the real number line. This is 0,
So
this is 1.
why is it 1.5? Why is it not 1.9? Let's say.
Because by convention, we use 0.5 to adjust.
Okay,
Because
so it always has to be by 0.5s?
Yeah, because this way, minus 0.5 and plus 0.5 is the same thing. If you use 0.9, then you have to use 0.1. That's not convenient and not consistent. Yeah, always use 0.5. Also, 0.5 is the middle point of any two consecutive whole numbers, right? Always have to be 0.5 right here. Yeah, if the calculator know, okay, for a continuous random variable, you are looking for the probability of the variable less than or equal to 1.5. You see that? Then you know the corresponding discrete random variable only assume 0 and 1, not including 2. I tried. Okay, so the upper is 1.5, not 2. Okay, if you enter 2, then you would have you will have the probability that you are not actually looking for that probability. You are looking for this probability. You would get this probability, which is not what you want. Yeah, what you want is strictly less than 2. And then the mu is gonna be right here. Okay, and then your sigma is gonna be right here, and your paste. Yeah. So let me repeat. Turn on your calculator. Go to second verse. In the distribution list, select normal CDF. Okay. The lower bound of the interval is a negative infinity. So you're gonna enter negative E99. We have been talking about that for a while. How do you find the negative sign, not the minus sign? How do you find the E, second comma, and 99? And your upper bound, very, very important. Yeah, we are learning how do we adjust the continuity, right? From discrete to continuous. How do we apply this continuity correction? So your upper bound is not 2. Your upper bound is 1.5 because here is strictly less than 2. And then your mu, enter 14 times 0.4. Your sigma is square root of 14 times 0.4 times 0.6. And then you paste. And let me know what you have. Yeah, this is the first question we see. How do we use the normal to approximate binomial? Yeah, same with mine, right? Very good. Thank you, Dustin, Kelly, and Miranda. Perfect. It's not horrible, right? I want to make sure that you understand me when I say we cannot enter 2 as the upper bound. Instead, we have to adjust that to 1.5. Is that clear? Okay, perfect. All right, so let's find some other similar problems to practice. This one is to find at least 5. Okay. Number 9. If NP no less than 5, NQ no less than 5, estimate this probability. So now we have a binomial with n equals 13, p equals 0.4. Yeah, we can quickly to double check if the two conditions are satisfied. 5.2. Yeah, n times p is 5.2, is bigger than 5. And n times q, 13 times 0.6, because 0.6 is even bigger than 0.4. So it's also bigger than 5. So yes, those two conditions are satisfied. All right. Yeah, as I said, you have other questions that they do not both satisfy, then you just choose the normal approximation is not suitable. All right. In this case, it's suitable because mainly we want to practice continuity correction. All right, so we are looking for the probability. So we are able to use the normal approximation, right? And the normal approximation we are using are going to have mu equals n times p. It's a formula we learned from previous section. And sigma equals square root n times p times q. All right, yeah. All right, so that's the normal distribution we are going to use to approximate the actual binomial distribution. And the probability we are looking for is the probability at least 5. You do have to know some algebra regarding those inequality notation. P at least is bigger than or equal to. All right, bigger than or equal to. So basically, the values that x could assume include 5, 6, 7, 8, 9, 10, 11, 12, all the way to, all right, yeah, that's the value x could assume. But as a continuous normal distributed variable x, how do we let the calculator know that? We would have to adjust and write a 5 as a 4.5. This way, the calculator know 5 is included. Yeah, the minimum whole number that x could assume is 5. 4 is not in it, but 5, yes. Does that make sense? So 4.5, not 5.5. If you do 5.5, then the calculator think 5 is excluded.
So sorry, for this one, it's P. I thought P is like translating at least 5 would be x is greater than or equal to 5. So I thought you would put 5 as your lower limit in this case.
Yeah. Yes.
You do? Okay.
Yeah. Yes. Yeah. But for a continuous random variable bigger than or equal to 5 and strictly bigger than 5, they are the same thing. The calculator wouldn't know. You have to let the calculator know that 5 is the smallest whole number the variable could assume. In order to do that, you have to adjust the 5 to 4.5 to make sure that the range, the interval, does include whole number 5 in it, but not 4. Does that make sense? So when you use,
I think so.
Let's go to calculator. Oh, okay, thank you. When you go to calculator, second vars distribution, normal CDF, your lower bound, I have a good news to pronounce that next time I'm going to bring the new laptop from work they gave me. And of course, I wish that is a touch screen and I can write it on it, but it's not touch screen, so I have to use a writing pad. The good news is that computer has the TI-84 emulator. That's the only thing I need. They wouldn't install the TI-84 emulator on my personal device. Even my personal device has the touch screen that I can write on it. It's pretty not inconvenient. Yeah, next time I'm gonna bring my new laptop and use the emulator to show you. Would be better, I believe. I hope, yeah. So lower you enter 4.5, upper you enter E99, and the mu is here, sigma is here, and paste. And let me know what you have. If you have been paying attention in the class, you know what I'm talking about. Otherwise, you wouldn't know. What is second vars? What is distribution list? What is a normal CDF? And let me know what you have. Yeah, exactly. Thank you, Miranda. That's awesome. Perfect. Oh, be careful the rounding. Yeah, the answer probably I think is correct. Yeah, be very careful with the rounding. Round to 3 decimal places are needed. Yeah. Any question about this problem? Yeah, thank you, Leah. I hope you all, have the same result. Yeah, I hope you have a TID for calculator. Otherwise, it's going to be very inconvenient. Use the table. Okay, awesome, Kayla. Perfect. Okay, no question about this problem? If not, I'm going to find a different one. Yeah, earlier we have this one is strictly less than 2. And this one is bigger than or equal to 5. It's different, right? Yeah, next I'm going to find also a different one. Let's see. Soon. So what is supposed to previous reading? Exactly. Okay. Let's do 11. Use a normal approximation to find the probability of the indicated number of voters. In this case, assume that 175 eligible voters aged from 18 to 24 are randomly selected. Suppose a previous study showed that among eligible voters aged 18 to 24, 22% of them voted. Yeah, this is the past data. This is the data from the history. Yeah, we're going to use that to be the P. Yeah, we do have a binomial here. We have a binomial. Let's identify the binomial. You randomly pick a voter and ask him the question, right? What is the question about? Oh, okay. Sorry. You randomly pick a person. Yeah. You randomly pick a eligible voters. The voter is eligible. The person is eligible to vote doesn't mean he actually voted, right? Yeah. So that's the thing. So let's say the first trial is you randomly select an eligible voter and ask him, did you vote or not, right? If he votes, that's success. The probability of success is 22%. This value is from the past. This value is from the past. And the Q, of course, is going to be 0.78, right? Yeah, N equals, yeah, and then you keep doing the same trial over and over again until you have 175 participants. So that is 175 trials. The number of trials is 175. Yeah, I don't have to do that. I know it's going to be past 5 for sure because this is a large number, right? Yeah, even 0.22 is a very small decimal. Yeah, it's around, yeah, and you multiply that, definitely is bigger than 5. So yeah, but you do have to check, by the way. Check both and make sure both of the two conditions are satisfied. In our case, they are satisfied. Okay, then now we're gonna go ahead to construct the normal distribution that we can use to approximate the binomial variable. Mu is n times p. is 175 times 0.22, and the sigma is square root NPQ is square root 175 times 0.22 times 0.78. And we are looking for what? Well, we are estimating what? Suppose so probability that we're estimating the probability that exactly 41 voted. Probability that we have exactly 41 voted. Okay. Yeah, you might wonder, why do we need to approximate when we actually could use the binomial function to find the exact value, right? It has its benefit, or in theory, this actually reveals the connection between the two distributions. Okay, so how do we apply the continuity correction? So the only whole number x assumed is 41. But if you enter the lower as 41 and the upper as 41, you can end up with 0. Yeah. So we have to adjust. Use an interval to represent the event that binomial variable exactly equal to 41. So this is bigger than or equal to 40.5, and this is less than or equal to 41.5. Yeah, use the 0.5 again. Use the 0.5 again. My mentioned earlier actually is similar with this one, right? This is real number line. On the real number, x only can assume we want x exactly equal to 41. We want an interval, yes, 40.5 and 41.5. So your lower is going to be 40.5, your upper is going to be 41.5. Your mu is here, your sigma is here. All right, guys, you ready to use your calculator? And let me know what you have. Your answer should be 0.0655 or 6.55%. Yeah, 0.655. Awesome. Very good, very good. You guys are great. Yeah, even every time we only have 3 or 4, a few participants share your answers, and the majority just keep silence. I hope you know what's going on and you are not actually wasting your time. All right. Yeah, I think, as I said, I don't want you to struggle. You are not mathematics major. Fortunately, you know, we have to struggle. The professor very, very strict, and think we are Superman and we don't need to sleep. We have to study all the time and prove all the time. I don't want you to struggle when you learn mathematics. So that's why the main purpose of my class is try to make your job easier when you do your homework. And your homework is strictly related to your score. And also the homework problems are from the same pool where your exam problems come from. So I hope this would help you with that purpose. And we run out of time. I would say good night. And Miranda, please, we can continue this section. I'm gonna stop recording, and I can answer some of your questions. And this morning, the technology didn't allow